Hey everyone, so this lecture we're going to talk about inverse functions. Now before I define what an inverse function is, I wanted to point out one function that will come up in just a little bit as sort of a mini theorem at the end. Now the identity function on a given set A is the function, and we'll define it with the notation for this will be I subscript A, and this will be a function from A to A, and it's defined in this way right here. So you give me an input x, and what this function is going to do is it'll just give you back that same input. So you give me x, it gives you back x. So this is the identity function. Now you're pretty familiar with this in some of your earlier algebra courses. You probably would have just written it as like f of x equals x, right? Something like that. Or you might, or let me move this over a little bit. So f of x equals x, or you might have written it as like y equals x if you were looking at like the graph of the function, right? Okay, so, but in general, the identity function on any set can be defined in this way. So we're just looking at it in a much, much more general context than what you saw maybe in algebra. Okay, now just like before, our functions are quite general now. But if you give me a bijection from A to B, then we can actually define the inverse function of f. And this will be the function, and the notation for this will be f superscript -1. So this doesn't mean take the reciprocal of the function. It's just this is special notation reserved for the inverse function. And this will be a function from b to a, and it pretty much will just undo what f does. So the definition will be exactly this. F inverse of y will be equal to x if and only if f of x is equal to y. So in this definition, we're assuming that this y lives in b and the output x lives in a. And you know what? Let me draw you a picture for this. So if, let's say, okay, so here's my set A, and here's my set B. Okay, so f is a function from a to b. So I have an x in a, and since I have f is a function from a to b, okay, it's going to take this x over here, and it's going to take it to f of x. And we could call that y, all right? So it takes it to this element. Now the inverse, it's going to undo this. So the inverse function should take this back to x. Now, how do we make sense of that? Well, what you can do is you can think of the inverse as a function from b to a, right? So now its domain will be the codomain of f, right? So these get flipped effectively, right? So the inputs for the inverse come from b, and they have to go over here to a. So this is how they're related to each other. And you see that this would be f inverse of y. So again, this little y is an element of b, and if I figure out where the inverse will take it, well, it should take it back to this. Okay, so they effectively undo what the other does, right? So f sends x to f of x, and then the inverse will bring that back to x. Okay, so if we call it y, then that element y will get sent to f inverse of y, which is x. Okay, now one question you might be asking is, well, why do we need f to be a bijection in order to have an inverse function like this? Well, let me just kind of draw some pictures here to kind of convince you of that. The book actually does a really good job of going into this in much more depth. But let me just draw a couple of pictures to maybe answer this. So why does f need to be a bijection for f inverse to exist? Okay, so let's just explore this one at a time. Well, to be a bijection, it has to be both one-to-one and onto. So if f is not one-to-one, let's draw a picture for that. So an example of a function where you would not be one-to-one is we'd have to have two distinct inputs that go to the same output. So your picture would look like this, right? You'd have A and B here. All right, now, but what would the inverse do? The inverse would have to be a function that sends elements from B, that would be the domain, to A, right? But naturally, the way that we have to have it defined, using up above, I would have to send this element to both of these as an output. And remember that a function, if you give me an input, it's only supposed to have one output, right? So one input will give you one output. That was part of the rule. So f inverse would not be well defined. Would not be well defined. Okay, so it would not be a well-defined function. All right, you could create a set or relations of pairs, but it will not satisfy the requirement of a function. Okay, and then similarly, if f is not onto, well, then you'd have to have a picture like this. Okay, so let's say, just for the sake of pictures, let's assume that it doesn't fail the one-to-one condition, so I actually will have distinct inputs going to distinct outputs. But let's say that I have an element that's not hit. Then this thing, again, if this is from A to B, so my f would be going in this direction, right? But your f inverse, if I switch colors here, just to be consistent, this would be your f inverse. F inverse, again, would not be a well-defined function again. And why is that? Well, to be a function, I have to be able to take any element of B, which is the domain, and I have to be able to assign it some output, right? But look at this. This element was not hit by f over here, because this is not onto, right? The range of f is not all of the codomain. There's some element that's not hit by this function. So this one right here would have no output for the inverse, right? So since this would have no output, that would not be a well-defined function, right? To be a function, everything in the domain has to have some kind of output. So because the original function was not onto, now I have this sort of missing condition here. Okay, so in both of these situations, the inverse function would just not be a function, all right, if it was not both one-to-one and onto. Now, you can actually fix some of these situations. Like if you have a function that is one-to-one that's not onto, you could actually restrict the function in a particular way. You could, so you can make certain kinds of restrictions in certain situations to actually fix the function, but in the end you'll want this bijection condition. Okay, so I won't go dive into that too much, but the book actually does a pretty good discussion on developing why this must be a bijection, and in summary I pretty much just showed you right here what's going on. Now moving on, let's take a look at an example. Suppose that I give you a function that's algebraically defined, right? So let's say that I give you this function, f of x is this nice rational function. Well, how would you actually find the inverse of this function? All right. Well, you might actually remember this procedure because in a lot of pre-calculus classes, this is actually part of the curriculum. But let me just sort of walk you through the procedure of how you could do this algebraically, actually. Okay, so the first step is what you do is you replace f of x with y. So you actually have y equals this rational, right? 2x plus 1 over 3 minus 5x. Okay, and then the next step, what you're going to do is you are going to swap x and y. Now, in this situation, you'll definitely always have one x here, but because the original function may have many instances of x, you're actually going to, you might have many instances of y when you do this swapping process. So replace all y's with x's and replace all the previous x's with y's, right? So just swap them completely. So just notice that. Okay, and then the next step is you're just going to solve for y. So you do that algebraically, right? So now we have to use some of our prerequisite knowledge. In order to solve for this y, I'm going to have to isolate it in some way. So the usual technique is you try to avoid fractions, right? So bring this over. So we have x times 3 minus 5y equals 2y plus 1. Multiply this up. Okay, or you're effectively multiplying both sides by 3 minus 5y, or cross multiplying, right? And distribute, so distribute this in. Okay, so we have 3x and then minus 5xy and equals 2y plus 1. And then the next step, what you try to do is you try to bring all the y's to one side of this. So let's bring, it doesn't matter which side you actually bring the y's to. You could bring all them always to the left or always to the right. Doesn't really matter. So notice that these two terms have y's in them. So let's bring them to one side. So let's just bring this 5xy to the right. Okay. So we have 3x equals 2y plus 1, and then we'll add that over. So plus 5xy. And what we want to do is just bring, we only want to have the terms with the y in it on this side. So we're going to bring this 1 over. So we'll have 3x minus 1 equals 2y plus 5xy. Okay, now that every term on the right has a y in it, you can factor it out. So that's the main reason you want to bring all those terms to one side. So then you have 2 plus 5x. 3x minus 1. And then now, you see the last step is, since I factored out that y, I can just divide by this extra term over here. So then you have 3x minus 1 over 2 plus 5x equals y. And so we did that. We solve for y. And then the very last step, all you're going to do is just replace y with the notation f inverse of x, right? So now you have f inverse of x is equal to what this y is equal to, so 3x minus 1 over 2 plus 5x. Okay, now in this problem, I just asked, how would you find the inverse of this given function? And we didn't actually confirm that it was 1-to-1 and onto, but we could explore that a little bit. You could use the standard procedure to show that it's 1-to-1 and onto. Another thing you can notice that from maybe some of your prerequisite classes is sometimes they ask you, if they give you a function of a real variable x, they might ask what's the natural domain, which is pretty much what are all the allowable inputs. So this function, since it's a rational, which is polynomial over polynomial, the only thing that would be a problem is if we divide it by 0. So the domain of this, the natural domain, would be all real numbers, except the x value that would make this happen, right? Okay, so if you solve for what would make the denominator equal to 0, so you'd have 3 equals 5x, so then divide by 5, so you'd have x equals 3/5. Okay, so that would mean that the domain is actually all real numbers except for this value. So you'd actually want x to not be equal to 3/5. Okay, so f would be a function from this domain. And then the neat thing is, actually, since you did all this work, the inverse is also actually a rational function. So you could actually look at this and you could ask, what's the domain of f inverse, right? So let me write that out, right? So the domain of f inverse, which will be the codomain of f, right? And up here, the domain of f, let me add that in. So the domain of f, which will also be the codomain of f inverse, right? These all get swapped, right? So the domain of f will be the codomain of f inverse, and the domain of f inverse will be the codomain of f. Okay, so I'll summarize that in just a second. But again, this is a rational function, so then what you could do is you could just say this will be, so the domain of this guy will be all real numbers, except when the denominator is 0, right? So 2 plus 5x equals 0. So just subtract, so 5x equals -2, so x would be -2 over 5. So then the domain would be all real numbers, but then x would not be equal to 2/5. So you see, you actually, by doing all this work, you actually have figured out what the domain and codomain of the original function should have been. So we can actually just say, so that is f was a function from So up above we said the domain was real numbers where x was not equal to 3/5, right? All right, 3/5. 3/5, yeah. And then it'll be to this set. So that would be the codomain of f. Okay, so f would go from this set to this set, and then f inverse will be the opposite, right? It'll go from here to here, right? That's the domain of f inverse. It'll go the other way. Okay, so yeah. I mean, you can write all that, but there's no need. Okay, in the next example, what I just wanted to look at is kind of an interesting feature of a function and its inverse. So if you consider the composition of these two, all right, so if you consider the composition in either order, something interesting will actually happen. So the previous function and its inverse are these two, right? So the previous functions. Notice what happens when we actually compute these two compositions. So f inverse of f of x, by definition, would be this, right? F inverse of f of x, and then we can I just kind of wrote out a lot of the work for the composition, since this is review from the composition section from before, right? So f of x, we would just replace it with its definition, and then you would substitute that in as an input for f inverse here. So each of these x's in the inverse would get replaced with this entire ratio, right? And then now you have to do a little bit of algebra. So first what you do is distribute this 3 and this 5, and then you're going to find common denominator. So you want to find a complete common denominator throughout the whole thing of 3 minus 5x. So you do that for each of these, and you combine them, and then once you have those common denominators, the denominator gets dropped because of the trick of when you have a fraction over a fraction, you'll multiply by the reciprocal of the denominator fraction. And slowly yet surely this will simplify really nicely, and you'll actually just get x. So what this is really just saying is if you take the composition of f inverse of f of x, you'll actually just get x back, which is effectively what the identity function does, right? And actually the same thing will happen if you figure out the composition in the other way, right? So if you do f compose f inverse of x, that actually can be computed, and you'll also get x. Okay, so just note that both these compositions yield the identity function on their respective domains. So remember, the identity function depends on what set you're talking about. So this one, f inverse of f, the input here would be x, and that would be in the domain of f. So that's why that would be the identity function on the domain of f, and then here the input would be in the domain of f inverse, and it would be that identity function. So in general, that's actually a theorem, right? So if you have A and B are non-empty sets and you have a nice bijection, then if you do this composition, f inverse of f of x, you'll just get back x. And same thing in the other order. So so this kind of makes sense of the idea of the inverse effectively undoing what f does. So you can kind of think of this as if you compose an inverse with the original function, they kind of get annihilated, and you just get back the original input. So nothing changes. So let me give you kind of an example where you have seen this probably in a past algebra course, right? So for example, if you have the function f from r to r, and the function defined by f of x equals x cubed, right? So the inverse action, if you're cubing something, the inverse would be to take the cube root of something. So if you actually do solve this, the inverse will be from r to r, and it'll be defined by f inverse of x is the cube root of x. And of course, if I do these compositions like we're saying up here, right, f inverse compose f of x, I mean, just let's write it out real quick for this example, right? So you would have, what's f of x? That's x cubed, right? So I have x cubed. Okay, and then now if I plug in x cubed into the inverse, then I'll have the cube root of x cubed. So just naturally from algebra, whenever you saw this kind of thing, right, that you thought of them as inverses, and so you're just going to get x back, right? So the cube root of the cube will get you x. Same thing will happen in the other direction, right? So if I do f compose f inverse of x, okay, so you write all this out. now you'll actually be taking the cube root of x cubed, and again, that's just written another way, but you see that you're composing the function in its inverse, and if I take the cube of the cube root, I'm going to get back x. So this actually does have some nice algebraic consequences. Another example where you may have seen this before is when we were talking about like logarithms, right? So for example, you could have a function r and exponentials, right? So from r to positive real numbers, and you could write this as the interval from 0 to infinity as well. You could defined by f of x equals, let's say, e to the x. Now this is the natural log base, right? So e is like approximately 2.718, so on and so forth, right? But you could actually pick any nice base here. So for like 2 to the x, and remember that the inverse for an exponential function, this is an example of an exponential, is the logarithm of that base. And in this situation, the logarithm for this one, this is the natural logarithm, so this is ln of x. Now if this was like, say, 2 to the x or 3 to the x, right, then this would be, the inverse would be log base 3 of x. Okay, and these will effectively undo what the other does. So let me just kind of write out the consequences of that real quick, because this actually gives you a nice algebraic result. For example, this would say that so we have f inverse of f of x, right? And this is f of x is e to the x. So this would say you have natural log of e to the x, and that's equal to x. So look at what's happening here. The natural log and the exponential kind of cancel, and you get back the input of x. But you see that this is actually a really nice algebraic property. Okay, and then similarly, the other one would also give you a nice algebraic property. You would have something that looks like this. You would end up with e to the ln of x is equal to x. Okay, so here's another algebraic property, but it really just comes from this relationship between a function and its inverse. So exponentials and logarithms will undo what the other does, right? So they'll kind of have this canceling effect because of this composition. Okay, another kind of interesting example is from trigonometry. If you look at the function f from r to r, and you defined by f of x equals sine of x, this by itself is actually not a bijection. So this is not a bijection. Well, why not? Well, there's actually lots of inputs, distinct inputs, that will have the same output. Okay, one way you could actually visualize that is if you actually look at the graph of sine, right? So if you do actually graph this thing, there are many inputs that have the same output. So everything right here that I'm putting dots on, if you input any of these x values, you will get an output of 0 for a lot of these. So for example, 0 will give you, if you plug in 0, sine of 0 is 0. This is in radians. And if you plug in pi, so sine of pi will also be 0. So you see these are two distinct inputs, but they have the same output of 0. So f of 0 is 0, and f of pi is 0. So not 1 to 1. Now, in a previous algebra class, you might have actually had your teacher say, oh, well, this is what's called the horizontal line test, right? So if you actually draw a horizontal line, and there are multiple instances where that horizontal line hits the function, then that fails to be 1 to 1. Okay. Now, the other thing that's a problem is that it's not onto, because you see that the codomain here is all real numbers. Okay. Not all real numbers are an output. In fact, if you give me an input, the output will always have to be between -1 and 1. So you don't have all possible real numbers as an output. So it's also not onto because of that reason. So what can you do? Well, you can actually fix the function. And the way that you really just fix the function is you just restrict where the domain and codomain are. So instead, if I define capital F as a function from, okay, so it's going to be from negative pi over 2 to pi over 2. Okay, and then this is including those two ends. And it will be to this set from negative 1 to 1. Okay, so set of real numbers here to set of real numbers here, defined by f of x is equal to sine of x. Now this is a bijection. And you can check that this will actually be a bijection. It'll be both 1 to 1 and onto. And once you make that restriction, you actually can find an inverse. And the inverse, you might remember from previous class, this is actually called arc sine, or the inverse sine. Sometimes it's written like that, and sometimes it's written like this. Okay. Again, this doesn't mean the reciprocal, like 1 over sine. That's not the inverse. It's the function that would undo this one. And this would be a function from negative 1 to 1, right? So the codomain now becomes the domain, and the domain of f becomes the codomain of the inverse. One last thing I want to just point out, you might have actually seen some of this in your previous courses. You can actually attach some geometric ideas here. Like, for example, if you actually do graph this function, okay, so the original one, if you actually graph x cubed, okay, the inverse function, if you actually draw the line of where y is equal to x, okay, so y is equal to x, this is f of x equals x cubed, then the inverse function will be the reflection of the blue line over that dotted line there, and that should be the graph of the inverse function. You might have heard of that property before. It's not the easiest thing to draw, but it would be something like this. All right, so this would be f inverse of x is the cube root of x. Okay, and a little bit easier one to actually draw is this e to the x and natural log, right? So e to the x, all exponential functions with a nice positive base greater than 1 would look like this. So this would be the graph of e to the x. Okay, if I put that dotted line where y is equal to x, and I reflect this curve over that line, you'll actually get the graph for the natural log function, so a logarithmic function, right? So that would look something like this. Okay, so this would be this inverse. And you could, the reason that this is kind of nice to just mention is, you know, that procedure up above where we talked about how do you actually find the inverse function. You remember how we swapped the role of x and y. So this is kind of how you're getting that reflection effect happening. Okay. One other thing, you can kind of explore it point by point as well. For example, in this exponential function, this point is on the curve, right? But then when you reflect over here, this point will be on that logarithmic curve. So if you just interchange the x and y, this will be on the logarithmic curve. Okay, and you can do the same thing for the arc sine. So here, you're not going to be drawing the entire sine function. You would just be drawing it for a small portion of it, right? So the small portion where it would remain 1 to 1, and then you'd force it to be onto, so the output set, the codomain and range, because it's going to be onto, will be the set from negative 1 to 1 inclusive.